Well, this is the first recording on the reactions of alkenes. We've looked at so far reactions of alkyl halides and how they react with nucleophiles, wherein the nucleophile either attacks a carbon to give substitution product or attacks a beta proton to give elimination product. At the same time the bromine's coming off or after the halogen or leaving group is coming off. So either SN2 or E2 as this is coming off, or this comes off first and the nucleophile, a weaker nucleophile, weaker base, comes in and attacks the carbon or the proton in an E1 SN1 reaction. So what we're wanting to do now is transition. We're still looking at polar reactions as our focus, but we're transitioning to a very different type of reaction. The alkyl halide we considered a outside nucleophile, or again a strong base that has the ability to act as a nucleophile, hit a carbon, or act as a base, hit a proton. But it was the functional group being attacked. The functional group, being the alkyl halide, was being attacked by an outside agent, the nucleophile. We're going to flip things here. The functional group we're talking about is going to be the nucleophile. He is going to be on the attacking side. He is not going to be attacked. That was our alkyl halide. In general, you should know the big difference between these two types of functional groups is that the alkyl halide is attacked by nucleophiles. But when we transition to alkenes, the alkenes are the nucleophiles and they attack electrophiles in polar reactions. Many textbooks will start with alkenes because there's just a limited way in which you start the reaction with alkenes. The pi electrons have to attack an electrophile. And there's really not a lot of variety in terms of the types of mechanistic steps you can have for that. There is a little bit more variety when we talk about nucleophiles attacking alkyl halides. The four reactions, SN2, E2, and then SN1, E1 kind of coming together. So there's kind of a lot of variety in terms of mechanism. Not so with alkenes. Alkenes in their polar reactions are a little simpler, at least in terms of number of mechanisms that are differing. The problem is the carbocation comes back into play when you have an alkene attacking electrophiles. Alkenes attacking electrophiles will see in some cases carbocations, and that can be difficult to predict the reactivity of or understand. It's like the SN1, E1. Students don't like those because they have carbocations and you can shift, things that add complexity. So let's go ahead and look at just one reaction, the acid reaction with an alkene. So the acid's going to be an inorganic acid such as HBr or HI. We could also use HCl. Inorganic acids where X is one of the halogens. So a very simple reaction involving one of these inorganic acids that are strong acids reacting with an alkene. So that's the first one we're going to look at. We'll fill in the rest of these boxes, the other polar reactions, these three. And then the last recording will be on oxidation reduction reactions. So we'll have three recordings. The first one just looking at addition of acid across a double bond, addition reactions. So we're needing to remember not only are we attacking the electrophile with the pi bond, as we talked about in with the last slide, we're going to have addition reactions, meaning 1 plus 1 comes together to make 1. 1 plus 1 comes together to make one molecule. So these are addition reactions. We'll also just at the very end of this first presentation just mention the anti-Markovnikov addition reaction you get as a radical reaction that we'll not look at the mechanism for. We're going to focus mostly on polar reactions and their mechanisms through the next three videos. The first one being on addition of acid. The second video will focus on 2 and 3, the polar reactions wherein we have something other than an acid added. And then the last one will focus on oxidation reduction. So let's look at just addition of HX. let's use HBr for our first example. HBr added to 2-methyl 2-butene. Here's our longest chain of carbons, so it's a butene. We have our double bond between carbons 2 and 3. And we number from this position because that's where our first branch is closest, is to this end. So we say 2-methyl 2-butene. How would this react with HBr? Well, the notes we want to put on our slide are strong acid. This is a strong acid, so we need to know that strong acids act as their name implies, they act as acids. They give up protons. So the first thing we need to remember is that if it's a strong acid, what would kill us in this strong acid if we drank it would not be the bromine as bromide, Br minus, but it would be the H plus, the acid. So that's the most reactive thing in this solution of the two, acid with an alkene. So the alkene is going to have to bring it. The alkene is not the best nucleophilic site, but it has pi electrons. Let me just pull out a model here of our structure here. Sorry, we had it right the first time. So let's propose this is our 3 methyl groups, 1, 2, 3, and we have our pi bond here in the middle. Alright, so it's planar, and the pi electrons we're going to use are above and below the plane of the 2 carbons that are connected in a double bond. So we don't show a sigma bond with this model here, but we kind of see a representation of above and below the plane of the pi bond. We have electron density that can be used to attack the proton. So this is at the very center, our nucleophilic site. In a sense, again, we're attacking from either face of the pi bond. So we always have 2 faces of the pi bond we could attack that proton with. That's here in blue. This proton we know is our electrophilic site. Now it can be full positive or it can be just still molecular, but either way it is the most reactive electrophilic site that you have in this solution of alkene with HBr. And I've just written it as H plus up here for practical purposes. You are dealing with a very strong acid. Somebody has to bind that proton. What do we have to bind it? Nothing else but pi electrons. So they bind that proton from either face. We're showing it from the top face of that pi bond. We could have used the bottom face. And we are left with an empty p orbital because one of these carbons picks the proton and binds it, and the other one loses those 2 electrons that were used to bind that proton. Now, which carbon do we put the positive on? There's a very important rule as we start our discussion of polar reactions of alkenes. It's the Markovnikov rule. We're going to keep it real general. We're going to go specific first as it was determined by Markovnikov. The proton always connects to the carbon with the most hydrogens. The proton. So the proton, let's go jumping down here to the mechanism. The proton is connected to the carbon with the most hydrogens. This one has 1, and we're talking about just the carbons in the double bond, not all of them. This carbon has 1 proton, this has none. So this carbon, the proton connects to the carbon with the most hydrogens, so the proton would connect here. And we can be more general in this rule and still and use it in a broader manner. We can just say the electrophilic site. Whatever the electrophilic site is that this alkene goes out and attacks, we always put the electrophilic site on the carbon with the most hydrogens. It's really not because of this carbon having any more nucleophilicity to attack the proton. It has to do more with the positive charge that's left behind. This positive charge would be most stable because it's tertiary. The carbon with positive is connected to 1, 2, 3 carbons. It would be a tertiary carbocation. So it's really about the stability of the positive charge left behind, not so much about this bond and the stability or strength of it. Now we're ready for our second step in this mechanism. So we make a high energy carbocation, and now we're coming down in energy. And we can bring the bromide in from the top. Just like there are 2 faces of a pi bond, there are 2 faces of a p orbital. We can bring it in on the top, of that p orbital or come in from the bottom. Now it doesn't matter because we don't have any stereochemical outcome from that. In other words, it's not going to be a chirality center. So we're just showing it from the top and we're done. That's not going to be the case on the next problem we're going to try that we're going to finish with. So let's review. First, we wanted to know that we have a strong acid. We tagged it. We put an H plus above that strong acid, knowing that this has to attack that proton. How do we place that proton on these two carbons? They're not shared. The proton does not share between these two carbons. Two electrons have to commit. Pi electrons have to commit one of the two carbons to the proton. Which carbon do we bond to that proton? Markovnikov rule. To the carbon with the most hydrogens. And after that carbocation is formed, the bromide left over in a second step bonds to the carbon that would have the positive charge. It can come in from one side or the other. We end then with an addition product. It is indeed just one product that came from two. Now it's best to know the mechanism for this reaction and how to quickly draw a product as shown up here. Putting the proton here and the bromine here. Now one last thing before we leave and try one problem using what we've learned. The Hammond postulate. We've heard this before in earlier recordings. It needs to be known that whatever carbocation is most stable, that is going to drive the addition reaction, because according to Hammond's postulate, the structure of the nearest transition state here resembles that of the nearest stable species, the carbocation. So whatever we can do to lower the energy of this carbocation lowers the energy of the rate limiting step, the highest energy of activation. This is the rate limiting step. So whatever carbocation is most stable dominates the direction of the reaction. All right, let's finish with this slide, at least our discussion of the mechanisms and the details of polar reactions. And then we'll finish with a anti-Markovnikov addition using radical reactions. 1-pentene plus HCl. So we need to make some notes. It may be best to draw this out. So 1-pentene, 1, 2, 3, 4, 5. That's pentene, but we need to know where the double bond is. It's 1-pentene, not 2-pentene, but 1-pentene. So it's between the 1 and 2 carbon. We're signifying that the double bond starts at the 1 carbon and bonds to the 2 carbon. So these reagents, we have plus HCl, are interacting, and we know this is a strong acid. Strong acid. So what do we have to remember? That gives up a proton. What has to happen then in this first step is somebody has to attack the proton, because this is a strong acid. R double bond. There's nothing else here. If we had a lone pair somewhere else on the structure, maybe that could attack the proton, but that's not what we have. We have just an alkene, 1-pentene. Where does that proton go? Let's remember Markovnikov rule. That proton goes to the carbon with the most hydrogens. One of these two that has the most hydrogens. Well, that would be carbon 1. It has 1, 2 hydrogens not shown. This one only has 1 hydrogen. So now we're ready to make our carbocation. This is a very important step of the reaction. This carbon, number 2, has an empty p orbital that can be attacked from either side. So we have an important step. We do not see a rearrangement of this carbocation. It's secondary. There's nothing better for it to be. So we're going to go ahead and go to product. We're going to come down in terms of energy. But we need to remember that we can come from either side. So as we draw our product, we can have that chlorine come from the backside. So this p orbital would really be coming straight out towards us. That chlorine can come from the backside. Let's get that 5th carbon in. This is pentene. Or it can come from the front side, that chloride, I should say, not chlorine. So that chloride can come in and attack two different ways. Now, again, I showed the p orbital from a side view, but if we have these carbons in the paper, that p orbital is sticking straight out towards you. So we can come in from the front, that would give us this product. Or we can come in from the back, that would give us this product. These are not the same. They are enantiomers. Enantiomers that are in a 50-50 mix is called a racemic mixture. Enantiomers that are in a 50-50 mix is called a racemic mixture. We must have that if we start off with achiral reagents. Achiral, meaning not chiral, cannot give us chirality. So you either have two options. Achiral reagents give achiral products as formed, or achiral reagents give us a racemic mixture. We're going to talk more about this as we go on in these two remaining presentations on alkenes. So we've finished. We have two products in a 50-50 mix because we started with achiral reagents and we ended up making chiral products. We had to have a racemic mixture. So let's go ahead and finish by not talking about it mechanistically. Let's just show how we could quickly go to product without discussion of the mechanism. We could put in our note strong acid, H+, a chiral reagent, just to kind of keep track of that. We could go ahead and show the product where we put the proton on the carbon that has the most hydrogens and the chlorine goes to the other carbon. So you can approach this just quickly going right to the regiochemistry. You could ask if this is chiral or achiral. Chiral or achiral. So you can break it down in steps. Oh, that's got a chirality center. So I know I don't really end with this representing the product. I must have, sorry, I'm drawing it. Should be 1-pentene. I keep wanting to draw butane. So we have to end with two that are in a 50-50 mix, these two enantiomers. Well, that's it. You can approach just going quickly to products using your notes about Markovnikov rule. This goes to the carbon with the most hydrogens and the chlorine goes to the inside carbon. Determine that you have chirality and say, oh, well, because it was achiral, I can't create a chiral product from an achiral reagent. I'll just draw two. But to understand that, of course, you would need to see that p orbital as being attacked from either side. Well, that's it. Just want to briefly mention that if we have peroxides added and HBr, these are very specific reagents. If we use very specifically HBr with peroxides, you go to an anti-Markovnikov addition. Just put in a note for yourself. Don't need to worry about mechanism. Anti-Markovnikov, meaning the proton, in a sense, we'll call it that. It's really just a hydrogen in radical reactions. Goes to the carbon with the least hydrogens. So it goes here, and the bromine goes here. That's it. That's what we're showing. Now, mechanistically, there's more to the story. It has to do with the radical stability that we initially make in the reaction. But I'd like to, for sake of time, leave it there as far as what needs to be known regarding the anti-Markovnikov addition of HBr to an alkene. If you see HBr and peroxide or some sort of initiator species, peroxides are typically used, you can have a whole lot of light, I guess, but peroxides and HBr, make sure you think, oh, it's not a polar reaction. We have anti-Markovnikov addition, meaning opposite of Markovnikov, addition of HBr. And that's shown above. The mechanism does involve formation of an alkyl radical initially where the H is going to be HBr is going to react in such a way that we have bromine coming in and initially attacking and leaving a radical behind. But that's something that this presentation will not focus on or not discuss. Bye-bye.